Hello and welcome to another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 9, Lesson 6 on spheres. All right, now this is the last lesson that we'll do in Unit 9, which is all about solids, their volumes, and their surface area. Today with spheres, we're only going to be looking at a sphere, what makes something a sphere, and also looking at its volume. We'll save the surface area of a sphere for later on in some other course, not in this one. But let's jump right into it and talk about what a sphere is. Now, there are many additional types of solids. I mean, there are so many out there: dodecahedrons, icosahedrons, tetrahedrons, lots of things with hedron at the end of it, hyperboloids, paraboloids. There's all sorts of stuff out there, okay? But the last one that we're going to look at in this course is the sphere. And honestly, essentially, a sphere is a three-dimensional circle. You more or less live on a sphere. I mean, the Earth isn't quite spherical, but it's pretty darn close. So let's talk about what a sphere is. A sphere is a surface consisting of all points that are an equal distance from a center point. That should sound a lot like a circle, right? A circle is all the points on a curve that lie equal distance from a center point. The sphere is exactly the same, except we don't confine it to a flat surface. We allow all those points to stretch out in a three-dimensional directions. Now, a segment drawn from the center to any point on the sphere, not surprisingly, is known as its radius. Just like the radius of a circle is the distance from its center to any point on the circle, the radius of a sphere is the distance from its center to any point on the sphere. So let's take a look at exercise 1 and talk a little bit more about a sphere before we get into how to calculate its volume. All right, here we go. Exercise number 1. A sphere is shown below, centered at point C with a radius of 5 centimeters. Now keep in mind what that means is every point on the sphere is 5 centimeters away from that center point. Various horizontal cross-sections have been drawn, including one that is 4 centimeters above the center. Letter A. What is true about all cross-sections that are drawn? All right, so what's true about every cross-section of this sphere that we drew? Pause the video now and write something down. Well, every cross-section is a circle. Every one of them. By the way, it's not that every horizontal cross-section is a circle. Literally, every cross-section is a circle. If I sliced off a part of a sphere using a flat plane in any direction, the cross-section I would see is a circle because every point on there would be the same distance away from that center point. Now let's take a look at letter B. Find the circumference of the largest circle that wraps around this sphere. Round to the nearest tenth of a centimeter. So I want to come up with the circumference of the largest circle that goes around the sphere, all right? See if you can figure out what that length is to the nearest tenth of a centimeter. Pause the video now. Well, the largest circle that's going to wrap around a sphere is one that's sort of, if you will, at the equator, or one that kind of goes through the north and the south poles. It's this circle, right? And that circle, right, has a circumference given by pi times the diameter, right? That's it, right? The circumference is pi times the diameter, which is going to be pi times 10 centimeters. The radius is 5 centimeters, so it's pi times 10 centimeters, in which case, let me bring this up a little bit farther, pi times 10 gives me 31.4 centimeters. I'm going to write this down. I'd suggest you do it as well. We can think about that as the equator, right? We could also think about it as what's known as a great circle, right? The largest circle that goes around a sphere is really sort of the length of the equator of the sphere, or likewise, if you sort of drew something that kind of went around it like that, which now I kind of want to get rid of. But yeah, 31.4 centimeters, right? It's just the circumference of the circle that has the same radius as that particular sphere. Now, let's get into something that's a little bit trickier. Letter C. What is the radius of the circular cross-section that's drawn 4 centimeters above the center of the sphere? Justify how you found your answer. So, the biggest circle that goes around this sphere has a radius of 5 centimeters. But what if I went 4 centimeters above the center of that circle and then drew a circle in? What would that radius be? Can you figure out how to find that? Pause the video now and see if you can think about it. Well, this is really cool, right? So think about this for a second. I'm going to take this picture and I'm going to pop it out, right? And by this picture, I mean I'm going to specifically take this and pop it out. Now, what do I know? Here I've got point C, right? Here I've got the radius of that circle, right? And here I've got 4 centimeters. Okay, and because I've gone completely vertical, right, from the center of the circle, and this circle is horizontal, then that's got to be a right angle. Now, I'm looking for that little length. It really feels like the Pythagorean theorem should kick in here. The problem with that, though, is for the Pythagorean theorem, I need to know 2 sides of this right triangle in order to figure out the third side that I'm missing. Well, I do know 2 sides of this triangle. I only put the 4 centimeters in because that's the only one labeled. But I actually also know this hypotenuse, right? Think about that. Why do I know that length? Pause the video now and think about that for a moment. Well, I claim that the length of that hypotenuse is also 5 centimeters. And the reason it's 5 centimeters is that this point lies on the sphere and therefore must be 5 centimeters away from the center of the sphere. That's a radii right there. No different than this radii right here. They both must be 5 centimeters, and now I can use the Pythagorean theorem. The Pythagorean theorem to find that missing side. And in fact, that missing side is a leg, so it's sort of my a squared if you want. R squared plus 4 squared is equal to 5 squared. You probably already know by this point what R is, but R squared plus 16 equals 25. Subtract 16 from both sides. R squared is equal to 9. Take the square root, and the R is 3 centimeters. By the way, we could do that for any circular cross-section at any height we wanted. All right? I chose this one because the radius of then that circular cross-section works out so nice. But we could do it at any point we wanted, even if we went just 1 centimeter up and we kind of wrapped it around. The difference then is that the picture would look more like this. 1 centimeter, 5 centimeters, 5 centimeters, and then I'd have to find the R that way, right? But the whole point of this is that that point up here must lie 5 centimeters from that point because all points on the sphere lie an equal distance from the center of the sphere. All right, now let's talk about how to calculate the volume of a sphere. Now there's kind of no getting around this. I have to just basically give you the formula. Now the volume of a sphere can be found using a formula that involves the number pi, no great surprise given its relationship to circles, right? So what is the volume of a cylinder? Well, the volume of a cylinder whose radius is r, and that's the only thing that matters about a cylinder, right? That dictates how big a cylinder is its radius. And its volume is simply the number 4/3 times the number pi times r cubed. That's a little bit small there on your screen, so let me write it a bit bigger. 4/3 pi times r to the third. Right, now without the 4/3 there, this looks a lot like the area formula for a circle, right? Except I got that r cubed, okay? Now, again, there's no way for me to really justify why there's a 4/3, but I hope you feel comfortable with the fact that it's r cubed instead of r squared, right? Think about the volume of a cube, right? That has an edge length of s. That would be s cubed, right? There's got to be three lengths multiplying each other. In this particular shape, it's r times r times r. Volume will always have three lengths multiplying each other, whether it's length, width, base, r, and h, you know, what have you. Here it's r times r times r. So let's figure out the volume in exercise number 2 of the sphere we were just working with. Let's take a look. Exercise number 2. Find the volume of the sphere shown above, or below in our case, to the nearest cubic centimeter. All right, let's do this together. This is real kind of plug and chug work. First, I'd like you to write down V equals 4/3 times pi times r cubed. All right, so one of the things that's great about a sphere is that the only number that matters is our radius, which in this case is 5. So we're going to have 4/3 pi times 5 cubed, and we're going to put it all in at once. Don't forget the pi, right? So we're going to do 4 divided by 3 for the fraction 4/3 times pi times 5 to the third. Now remember, to get that to the third power, we have to use what's known as the caret button. All right, most scientific calculators don't have a button on them that just naturally allows you to cube the way that there's a squaring button. But this little button, right, where we put it in as 5 caret 3 means 5 to the third. Now, once I hit enter on that, it then gives me my volume. Let me get rid of this so I can actually write my volume down. My volume will be 523.59, etc. We want to round just to the nearest cubic centimeter, so my volume is 524 cubic centimeters. Yep, that's it. So it's not very hard. In fact, in the grander scheme of things, I don't know what just happened there. There we go. In the grander scheme of things, finding the volume of a sphere might be the easiest volume we find outside of the volume of a cube, right? We simply do 4/3 times the number pi, right? That obnoxious 3.141592 kind of number, times the radius cubed, all right? It's a plug and chug formula. Now, just because it's a plug and chug formula doesn't mean you can't make some sense of it. Now, spheres are the equivalent of a three-dimensional circle. It's interesting to compare their volumes to the areas of circles. So let's do that a little bit, just so that we can feel a bit more comfortable with the volume formula of a sphere. Let's take a look at exercise number 3. A sphere and a circle, both with radii given by r, are shown pictured below along with the volume and area formulas for each, i.e. the volume formula for a sphere and the area formula for a circle. Letter A, name 2 similarities between the two formulas, and B, name 2 differences between the formulas. All right, so I'd like you to do both of these. Compare and contrast. I believe that there are 2 distinct similarities between the formulas and 2 distinct differences. See if you can list them. Pause the video now. All right, well, similarities. Let's go with these. 1, they both contain the number pi. And the number pi is all about circles, right? That's how you were first introduced to it, and pretty much that's how it will always kind of show up, is with things that have circles. And the other thing, they both only contain the variable r. In other words, right, you've got some formulas, let's say like the formula for the volume of a prism, length times width times height. That has 3 different quantities in it, length, width, and height. Or the volume formula for a cylinder, pi times r squared times h. That involves both r and h. But a sphere and a circle only depend, the only thing that changes in them is the value of the radius, right? So they both contain a pi and they both contain an r. So what are the differences? Well, one huge difference is area has r squared while volume has r cubed. And that's a big, big difference. In fact, one of the major mistakes I see that kids do, and I even do this on occasion, and I've been doing a lot of math for a long, long time. But what I see a lot of kids will do on occasion is instead of cubing the r with the volume formula of a sphere, they'll only square it, right? Because they're so used to the area of a circle being pi r squared that they see that pi r cubed and it doesn't become cubed, it just becomes squared again. And of course the other piece is that, and let me move my little eMath instruction logo over here, right? The other piece is the volume includes a 4/3 factor. Right? It'd be great if it didn't. It would be so beautiful if the volume formula of a sphere was pi r cubed. It would just make it so easy. It'd be like, well, pi r squared for a circle, 2 dimensions, pi r cubed for a sphere, 3 dimensions. But unfortunately, it's not that simple. We get that 4/3 thrown in, which is barely bigger than 1, right? 4/3 is 1 and 1/3, but it's there. What are you going to do? So let's use it a little bit more. All right, let's take a look. Exercise number 4. Given the volume of a sphere formula, V equals 4/3 pi r cubed, find the volume of spheres with the following radii. Show your substitutions, round to the nearest whole unit. All right, great. Again, this is just formula kind of plugging. So let's do letter A together, then have you do B and C on your own and see if you can get it right. All right, let's do it. So I'm going to put down V equals 4/3 pi r cubed. So in the case when r is 12, I'm going to have 4/3 pi times 12 to the third. And then we're going to do everything else on the calculator. 4 divided by 3 times pi times 12. I use that caret button to get to my third power. Enter, and rather large, rounded to the nearest whole number, 7,238, what do we have? Cubic feet. Cubic feet, remember, get those volume units in there. All right, but that's it. Right? It's actually very, very easy to do, even given our kind of scientific calculators, very simple. We just have to be careful about making sure we get everything in there. Make sure you have the pi, make sure you're raising it to the third power, not just squaring it, right? But then the rest of it is letting the calculator do its work. So try to find the volume when the radius is 3 centimeters and when the radius is 25 inches. Don't forget to put proper units on. Pause the video now. All right, let's do it. V equals, I'm going to keep writing down the formula, 4/3 pi r to the third. So the volume is 4/3 pi times 3 to the third. Let's clear this out. 4/3 times pi times 3 raised to the third gives me a volume of 113 cubic centimeters. Okay. And now let's take a look at this one. Volume equals 4/3 pi r cubed, which is 4/3 pi times 25 to the third. This one's going to be rather large. 4/3 times pi. It's going to be rather large because 25 to the third is rather large. All right. Oh, look at that. And the volume is 65,450 rounded to the nearest cubic inch. 65,450. Again, not the hardest formula to use. I think if I had to compare this to finding the surface area of a cylinder, I'd take this every time, right? But it still is a formula that we have to become proficient with. So let's take a look at one final problem. All right. Now, one of the most common things to do with spheres is to take half of a sphere. Now, we call those hemispheres. right? It'd be nice if we just called them half spheres, but we call them hemispheres. And you've heard that term before, right? When they talk about the northern hemisphere and the southern hemisphere on the Earth, right? That's what they're talking about. They're saying, hey, take the Earth, cut it at its equator, and you've got the northern hemisphere or the southern hemisphere. So let's do one final problem with a hemisphere. Exercise number 6. A tent has the shape of a hemisphere shown below with a base diameter of 10 feet. Letter A. How tall is the tallest person who can stand upright in the tent? All right, I love this question. All right, so like literally, if there was a tent that was a hemisphere, and many tents, although aren't perfect hemispheres, they can be approximated with the shape of a hemisphere. What's the tallest a person could be if they wanted to stand upright in this tent? Pause the video now and see if you can answer this question. Well, obviously the greatest height occurs right from the center of that circle up here. But that height is the radius of that sphere, and that's just 5 feet. I mean, if somehow we could have a tent that was in the shape of a complete sphere, then we could have somebody that was 10 feet tall. That would be a very tall person. But someone who was 10 feet tall, right, in this tent. Now, we could have a 10-foot tall person, again, a very tall person, lie down in the tent, right? But if I'm just going to stand up in the tent, I'm going to have a problem because I'm 6 feet 2 inches tall, and that tent's only 5 feet tall. All right, let's take a look at letter B. How much floor area to the nearest square foot does the tent have? So in other words, like, how much space do I have at the bottom of the tent to lay out all my junk? All my nutrition bars and my sleeping bag and my camp stove. Hopefully I'm not using that in the tent, but whatever. Try to figure out that floor area of the hemisphere. Well, quite frankly, that's just the area of a circle whose radius is 5 feet, right? That's it. It's just area equals pi r squared, where the r is 5. So let's find that out, right? No cubing here because we're just doing the area of the floor, and the floor is a circle. So it's got 79 square feet to the nearest square foot. Okay, now finally, what is the volume inside the tent, round to the nearest cubic foot? Now you know that the volume of a sphere is 4/3 times pi times r to the third, r cubed. This is half of a sphere. See if you can figure out the volume of this hemisphere. All right, well I'm going to do it all at once, okay? And you can do it in stages. Now we know that the volume of a sphere is 4/3 times pi times r cubed. Now notice, I left a little space here, and the reason I did that is that I'm going to throw in a factor of 1/2. All right? This is a hemisphere. It's only got half the volume of my original sphere. So I'm going to do 1/2 times 4/3 times pi times r cubed. Now, if you actually did 4/3 times pi times 5 cubed, got an answer, then divided by 2 and got an answer, awesome. There's nothing wrong with that, okay? I'm just going to do it all at once. Here we go. Right, last problem of the lesson. 1/2 times 4/3 times pi times 5 to the third gives me 262, rounded to the nearest cubic foot. 262 cubic feet. All right, that's it. Again, absolutely nothing wrong with first figuring out what 4/3 pi r cubed would be equal to, then dividing your answer by 2 because you've only got half of a sphere. That's a great way to do it. Let's wrap this thing up. So, the last three-dimensional solid that you see in middle school is the sphere. And it is one of the most magical shapes in the entire universe. And maybe magical is the wrong word for it, but when you look around and you look at soap bubbles, right, to the sun to the earth, all the planets, right? There are so many things in our universe that naturally take on the shape of a sphere because it's such an amazing object. Every cross-section of a sphere is circular, right? And its volume, no great surprise, can be calculated using a formula that involves both pi and the radius of the sphere. That formula happens to be 4/3 times pi r cubed, right? We're not surprised by the pi or the r cubed. The 4/3 is a little weird, but thankfully you'll be given that formula anytime you need to calculate the volume of a sphere. All right, well, I just want to thank you for joining me for another NGen Math 8 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.